Today we will discuss a different case of asymptotic estimate in a complex plane. Namely, we again consider a Laplace type integral taking along the contour in some complex along some contour in a complex plane. But this time our f of x function doesn't have saddles in a complex plane. The typical situation is when we deal with the contour which is semi-infinite. This is one possible situation, or quite typical situation, either Hankel type contour. So we have a branch point somewhere, the branch cut, the branch cut is directed, for example, in some direction. Generally, it's a curve, and the contour is a Hankel type contour. So how do we build the asymptotic in this case? Well, to understand what is happening, let's actually make a suitable change of variables. So this is, of course, the complex plane of complex variable x. And let's call this initial point here x naught, and here x naught again. Then the suitable change of variables is as follows. Well, let's denote this f of x naught number as tau naught. Naturally, that kind of change performs a conformal mapping from complex plane x to complex plane t. If x equals to x naught, then t is equal to 0. So after this conformal mapping, the contour is changed accordingly. And let's address probably the most typical case is when we deal with Hankel type contour. And because after the discussion is over, you will realize how to perform the asymptotic estimate for a simpler contour, which is here. Right, so here is our new complex plane. And the branch point is mapped onto t equals 0. The branch cuts say, of course, it will change its direction, and now it will start in the downward direction, for example. And the contour will change accordingly. Now let's see what's going to happen with the integral itself. F of x is now equal to tau plus tau naught, and x is f minus 1 of tau plus tau naught. And let's switch to this new variable tau. So dx is, of course, f minus 1 prime d tau, and function g of x is turned into the function of g of tau. So after this change, the integral is simplified and becomes the following expression. So generally, the simplification, in particular, it addresses the exponent form. Now the exponent is particularly simple. It's just lambda tau plus lambda f of x naught. And here we have g of f minus 1 of tau plus tau naught times f minus 1 prime d tau. And let's call this function h of tau. So now we have a simplified integral, and with particular suitable exponent. Now it's just lambda tau. We can factor out lambda f of x naught and put it in front of our integral. And let's call this contour now gamma prime. Right. And since we have the simpler exponential, let's analyze how the asymptotic is built. So lambda, for concreteness, lambda is supposed to be positive and large. So the steepest descent direction for the exponent is simply, well, let's just, so it's a imaginary part of lambda tau is constant line. But we realize, of course, that the crucial point for the whole integral is the vicinity of this tau equals to 0 point, the origin. Why? Because it's the point where the exponential is maximum. Well, of course, there are other points where exponential is even greater, but the general slope of the real part of the exponent function, it's a downward slope. So it's like a plane inclined in this direction. And for example, we could deform the contour like this, where the exponential function is great. But since there is no branch cut here, this contribution to the integral, they will cancel each other when we go to the right and return from the right to the left. So it is the vicinity of this point which makes the essential contribution. And at point t equals 0, the imaginary part, the whole function, the whole exponent function is 0, so the imaginary part is 0. And as a result, the steepest descent line is this. So unsurprisingly, it's this negative tau direction. And accordingly, the contour should be deformed in such a way that it passes, so it arrives at this branch point along the steepest descent direction and leaves it in the same direction. Well, at least for the upper bank part of the contour, there is no problem to deform it in the steepest descent direction. We just rotate it slightly like that, and here it is. Right, that's the steepest descent direction, and we just deform the contour like that. However, with the lower part of the contour, there is a problem. Why? Because the position of the branch cut forbids the contour to be deformed into this negative direction line. So what are we supposed to do? Well, fortunately, we understand that so there is a branch cut. That means that this g function is a multi-valued function, and so we should see this function as the function defined on some kind of on a set of Riemann sheets, and this branch cut is in fact the connection between the upper Riemann sheet and the lower Riemann sheet. So in fact, we can cross the branch cut, and the contour can cross it, but the continuation of the contour will belong to the lower branch cut or upper branch cut, depending on the situation of the second Riemann sheet, which is, for example, if it's below, then it's below the upper Riemann sheet, which is depicted on the blackboard. So let me show you with the visualization of the situation on my laptop. Так, и сейчас идет визуализация с моим комментарием. So that's the Riemann surface, the typical Riemann surface of the g of tau function. And here is the position of the branch cut. And this is the deformation of the contour, which basically performs the trick which we just discussed. Like that. So here we go. Now let's actually compute the integral and find the final explicit expression for the asymptotic series for this integral. And finally, let's analyze in some more detail what's going to happen with the argument of our tau complex variable when we cross this forbidden region of the defined by the position of the branch cut. Well, initially, our tau are defined by the following values of the argument. Well, suppose this angle here at the origin is alpha, and the argument of tau initially belongs to the region from pi minus alpha. Oh, sorry. This is a pi minus alpha angle, but since we move in this clockwise direction, it's minus pi plus alpha. And on the top, it reaches the value of pi plus alpha. However, after the deformation of our contour, here, as you see, the upper part of the contour leaves the origin in pi direction. But the lower part, here is, I drew it with a dashed line because it belongs to the lower Riemann sheet. So the lower part arrives at the origin in minus pi direction because this is minus pi plus alpha, and it just rotates a little bit more into this minus alpha direction, so it's minus pi plus alpha minus alpha. So it arrives here at minus pi direction. That's it. That's the only difference. Otherwise, it's just very simple. And how do we perform the estimate? Well, we just realizing that the crucial contribution comes from the origin in T-complex plane. We expand our h of tau function, which is multi-valued, in the vicinity of the origin. The expansion, in its most general form, looks as follows. So it's almost Taylor-like expansion, but the powers, not just n, but n plus some real, not necessarily, but some plus some number s, where s may be real or even complex power. So that's the Taylor expansion in the most general form. Now we plug it in into our initial integral and just perform the integration, because the integration becomes elementary due to the simplicity of the exponent here and pre-exponential factor, which is tau to n plus s. So here we go. The integral is split, decomposed into the sum of very simple integrals. And each of these integrals is just the integral along the Hankel contour. And as you remember, it's a gamma function up to 2 pi I term. Well, naturally, there is additional lambda factor here, so it becomes a gamma function after the rescaling lambda tau equals to v, for example. Once you perform this rescaling, what you eventually arrive at is 2 pi I divided by the gamma function of minus n minus s, and divided by lambda to n plus s plus 1. And naturally, there is a prefactor. Sorry, I actually dropped it here. So the prefactor is e to lambda f of x naught. Here it is, and here, of course, it is. And here it is in front of our sum. So here is how the general asymptotic estimate is made. And the procedure is quite general, and you can use it with any type of the integral. Well, sometimes in the textbooks, this gamma function in the denominator is substituted with gamma function in numerator with the help of so-called mirror identity. And indeed, gamma function of n plus s plus 1 is simply pi divided by gamma function of minus n minus s multiplied by sine of pi n plus s with negative sign here. So we can substitute it and arrive at the just more canonical expression with gamma function in the numerator. And this series, by the way, is usually an asymptotic series. And sometimes the whole asymptotic method, which was just discussed, is called the Watson lemma in asymptotic analysis. Right, so then just one of the ways to perform that kind of estimates when our f of x function doesn't have saddles in the complex plane, or for some reason these saddles are unreachable in our problem. There is another treatment which is almost identical to this one, and let me show it to you in just 2 minutes. And another quite analogous way to look at the deformation of the contour, but without the slipping on the lower Riemann sheet of the Riemann surface of the multivalued function, looks as follows. So again, we have the initial position of the branch cut. Here it's just inclined slightly below. But what you can actually do is to deform the branch cut in such a way that it obeys the position of the steepest descent of the contour. So for example, for this picture, that would mean since our steepest descent direction is pi, negative real axis of tau, then what we do, we deform the branch cut itself. Of course, as you understand, the crucial tau for this integral are the vicinity of the origin. So actually, you need to deform the branch cut direction just in the vicinity of the origin, and then it can continue in the same way as it was before. But once you've done this, you don't have to include another Riemann sheet in your consideration. And sometimes it just helps you avoid unnecessary complexity of your problem. Because now your contour belongs entirely to the upper Riemann sheet. And of course, the rest of the consideration is just completely identical to what we just discussed before, and you arrive at the same answer, just word by word, you reproduce the same kind of expression. So that's it. Use it at your convenience. Sometimes just it's more natural to slip on the other Riemann sheet of your Riemann surface to build the asymptotic estimate. But sometimes you just bend the branch cut and arrive at the same identical expression. But of course, in the latter case, you need to change the allowed regions of your argument. Sometimes because in most cases they are fixed initially by some physical condition of your problem. Here you just change them slightly, but it's just completely equivalent way to look at the same problem.